Okay, we reached the magical number of 30. And yes, hello, ladies and gentlemen, and welcome to another EPICentre seminar, the online edition. We will have Professor Dina Dayala today to introduce the session as well as our speaker. So Dina, the floor is all yours.
Thank you very much, Arash. So welcome everybody to this new addition to the EPICentre Seminars online editions. I hope you are all well and you are enjoying as much as possible working and living in remote. Today's seminars is presented by Ahsana Parammal Vatteri. She's a PhD student in her final year in the write-up period. And she has worked with me for the past 4 years on looking at the multi-hazard analysis and assessment of school buildings at risk from earthquake and floods with a specific application to the north region of India, where both hazards are very prominent, given the combination of the position at the boundary between the Indian subduction zones and the wonderful Ganges basins, which floods every year together during the monsoon season. Ahsana is an exceptional student and researcher. She has been working with us at UCL through the prestigious graduate research scholarship, overseas research scholarship, which she was awarded 4 years ago. With this, without any further ado, Ahsana, please go ahead and enlighten us about your approach to multi-hazard risk assessment.
Thank you, Dina. Thank you so much for the introduction. And thank you, Arash, for this opportunity to share my research for the past 4 years with you. Today, I would just start sharing my screen. Hope this is now clear, visible.
Yes, it is.
Yeah. So today we're looking at the of a particular typology of masonry buildings with flexible diaphragms. The typology is known as confined masonry. So first of all, we would look into this typology in a little bit of a detail and see if the buildings that we are looking at are indeed confined masonry, or if it is, to what extent. Secondly, we would look into, two very important aspects of analyzing any existing building stock for their seismic behavior. So we try to develop a taxonomy system that would identify the features of seismic resistant features of these buildings. And then we apply seismic performance and fragility analysis techniques. So these, you could use standard procedures and techniques for these, but I would like to highlight some of the challenges that I came across doing this. And I think that this would be helpful for the students who are joining our MSc programs and others who are doing similar kind of work. So in the end, in the very final bit, I would like to just give a hint of like how we are going to use these fragility curves for the multi-hazard approach Dina has mentioned in the introduction. With that, if you are into this topic, you could look out for this publication that is recently accepted with the results that I'm presenting today. So coming to this typology, many of you might be familiar with this. The confined masonry is the typology that is in existence for now for more than 50 years in countries like Mexico, Chile, and Peru, where the seismic hazard is really significant. This is a typology that is developed primarily from the site and then adapted to standards and codification, and now there are national and international guidelines available for this. So what it consists of is unreinforced masonry panels confined by lightly reinforced concrete elements, which tie them together like a box. So primarily, these are used for residential buildings, up to 4 or 5-story flat structures even. But increasingly, this is being used for school structures. And as you might be aware, school buildings are inherently more vulnerable to seismic hazards because of their larger spans and larger openings and so on. So we are looking into this very interesting typology in the context of school buildings. And also the other thing is, because this is a typology primarily originated from site and improvised over time, you can see a lot of variability within this typology around the world. So we try to incorporate our attempt into how well you can classify them, the non-engineered confined masonry construction practice around the world. So these kind of buildings, in the first instance, they look very similar to an RC frame structure with masonry infills. So how are they different, or are they any different? So if you look in the figure on the left, the RC and CM, that's a confined masonry construction, primarily differs in a number of ways. First one is the sequence of construction. So if you have noticed from the previous video, this is in the confined masonry, you build the masonry walls first, sometimes even leaving toothed edges, and then cast the RC elements. So you can imagine the kind of bond that would create between the RC and the masonry. On the other hand, in RC, you create the frames first and then do the infills. Also, there is significant difference in the relative stiffness and relative size of these elements, and also reinforcement. And also, when it comes to lateral action, there is significant variation because the CM walls act more like shear walls, while the RC infills act more like contraction struts. So when it comes to the RC confining elements, those are the ones that is providing the added ductility of these wall panels, even while masonry being a stiff structural element. So what happens is when the load starts loading on the wall, initially the stiffness and strength of the confined masonry panel increases and then drops following the onset of the diagonal cracks, where you can see the 0.1, for example. And it still keeps on taking further load until the critical regions of these RC elements are damaged. And it only starts reducing, I mean, the stiffness and the capacity drops beyond that point. So by this time, you have a significant ductility or the deformability that is available for the structure. So now we look into the specific typology that we see in India. We were fortunate to find this database of existing school buildings in this particular city called Guwahati in Assam, very close to the Himalayas. And we see that there are a number of buildings, at least this database says that around 60% of the buildings are confined masonry, which is a surprising factor because no confined masonry guidelines were available in India at the time of their construction. So these are is mostly single-story structures with flexible diaphragms with certain level of confinement. So if you can see, some have sill bands around the lintel level, around the plinth level, some even has at the sill level, and also they have columns, RC columns at intervals not more than 3 or 4 meters. So they fall into this category of confined masonry buildings, not conforming to all the standard guidelines a confined masonry would require. So the next step was to see the level of how much this conforms to these kind of typologies. So we developed this very quick tool for assessing the level of conformation to these existing CM guidelines. We checked with the international guideline by EERI and also National Building Code from India. So bear in mind that this National Building Code was only released in 2016 and these buildings are at least 30 or 40 years old. So these, when at the time of their construction, even though they were not they were not conforming to all the guidelines by these standards, they do. What we see from the comparison is that most of the dimensional requirements are satisfied. Although we are not completely sure about the quality of connection. So only in the very rare cases where you have an unplastered wall, you are in a position to make a judgment on which element was first cast and which was then. So although it conforms to dimensional requirements, we find that there are some very important factors that are missing in these buildings. For example, they don't have cross walls at the required spacing, or they don't have confinement around openings, which is required for a standard confined masonry building. And also, because they are flexible roof buildings, they are supposed to have at least a roof band at the top, which is missing in most cases. So we see that these buildings could be somewhere in between the guidelines that were provided at the time of construction, that is IS 4326, which gives the seismic strengthening of masonry buildings in the form of seismic bands and some seismic vertical elements, the tie elements. But these are not fully conforming to either of these, but we could still check their performance as a confined masonry building. For this, we wanted to incorporate a taxonomy system that could actually identify their available features and recognize their deficiencies. So we used this global library of school infrastructure, a GLOSSy system as a base, which was developed also at UCL for a World Bank project. So we see that out of the 12 parameters the GLOSSy system, the original GLOSSy system has, we could still go with the same definitions for at least 8 of them. And we see that 4 of them requires modifications, mainly the main structural system, seismic design level, wall panel lengths, and wall opening sizes. So definitions and attributes of these are modified to incorporate these features of the confined masonry buildings. Now, we see that the seismic design level is the most important parameter that distinguishes between non-engineered and engineered confined masonry buildings. Initially, we thought of defining this design level based on 2 factors. That is the connection at the masonry or tie column junctions, and also the minimum required confinement. So whether the panel is confined on all 4 sides or not. So then we found that this alone is not sufficient, because having 2 things at the edges may not save the purpose of a confined masonry always, as you can see from the bottom figure on the D. So you need to have good connections between the tie elements, and the masonry, and also with horizontal and vertical tie elements themselves. So that is one of the main features. And the other one is the minimum required confinement, which would be the very base definition that would define whether the building is confined masonry or not, whether it has at least the major load-bearing wall portion has confinement on all the 4 sides. And the third factor is the wall density, which is a very common term used in confined masonry literature, which is nothing but the area of wall in a particular direction divided by the floor area. So depending upon the seismic hazard level and the soil type and the construction material and so on, each of these guidelines would give you a value for that. So you could check with this whether it's available, good, better design, not available, poorer design. So based on the availability of these features, we define at least 4 design levels from poor to high. And you can use this decision chart to decide the first 3 of them. And the highest design level requires all these criteria to be satisfied more than the minimum required level. And also in the case of flexible roof buildings, you have to have some stiffening elements at the horizontal stiffening elements at the roof level, so that it has a box mechanism. So in the case of this connection that I was mentioning before, ideally it should be built this way. You build the masonry wall portion first and then cast the concrete so that you have better connection. But once the building is built, you have no idea of knowing if this was done this way or the other way. So only in the case of when unplastered walls are visible, you can have some judgment on depending upon the roughness on the interface. Now, coming to the other two factors, the wall openings is another very important criteria, which has proven to be critical in the past earthquakes, sometimes causing partial or even complete collapse. So what is the criteria? Like the confined masonry guidelines tell you, you need to have confinement around large openings. Again, the large by definition varies between national codes from 5 to say 35%. And the guideline by ERI, they give you a criteria based on experiments as 10%. So for school buildings, it is not really practical to have such small openings, less than 10%. So what is recommended would be to have larger openings, but confined. So in the taxonomy, we have three such attributes, that is small openings, large openings with confinement, and large openings without confinement. Similarly, there is this wall panel length that is to be defined separately for confined masonry buildings, because this is defined in terms of the spacing of the tie columns rather than the cross walls. Although both are very important criteria, and we would see this as we go into the analysis. Now, based on all of these definitions, we have then identified at least 6 index buildings based on these 12 parameters, and we clubbed their taxonomy strings together to see what percentage of buildings are belonging to each of these index building typology. We see that the most important parameters that define or distinguish between them are the level of seismic design and the plan irregularity. So the first 3 buildings here, IB1, IB2, and IB3, have varying seismic design level from poor, low to medium, and remaining all other factors same. And the next 3 have the same different poor, low, medium design levels with horizontal irregularity. Some typical floor plans are given here. And we now look more closely into the first 3, which are kind of dominating the population of school buildings that we have assessed. So once we have these index buildings, what's the next step? You want to be able to assess their capacity through a numerical platform. So we have heard of, we have used finite element or discrete methods before. And what we used in this study is called an applied element method, which actually combines both beneficial aspects of finite and discrete element methods. So what it does is, you can discretize your structure into elements, rigid elements that are connected by normal and shear springs. And these are distributed along the edges of these elements, as you can see in this figure. So these springs actually capture the stress and strains due to the loading in the volume of a material that is attributed to each of these springs. And the elements themselves are rigid elements, and the deformation, stress, and strain are captured through the springs. And the material properties that you input for each of the material will be transferred as a property of the spring. So now we have 2 criteria based on which you will have cracks or permanent cracks or open cracks. So this is the good thing about this approach, is that you do not need to require predefined modes of failure or predefined crack locations. So it actually allows you to have collapse analysis up to collapse stage. So how it does is that it has a stress-based and a strain-based criteria. And when the stress exceeds material capacity that you have given for a material, the open crack starts forming. And it extends to a particular level where the strains are exceeded more than a given separation strain value. So only after the separation strain is exceeded, the springs go invalid or broken. So this actually happens organically in the analysis. So this is from one of our masonry walls, and you can see the springs that are forming between the brick and mortar. So when you have an interface element that will have an equivalent property, either you input it as an equivalent property, or you can find out an equivalent property for the material. So based on this, now we model the 3 index buildings that we have identified. And you can see this IB2 is not different from IB1 other than having better connections at the column and masonry interfaces. And IB3 has better confinement and better connections. Now, coming to this again, once you have the models, you want to be able to do a pushover analysis the simplest way possible. But then if you remember, they all have flexible roofs, and you have this issue with where do you apply the load or displacement. So we tried different ways. We first went back to a simple wall, which we used for validating in the first place. And we tried using a force-based concentrated pushover here at the top beam, which was replicating the experimental envelope pretty well. And then we tried distributing the load across along the height of the wall. And to get the same displacement levels, you need to have higher levels of loading. And finally, we applied a ground acceleration that's very similar to actual earthquake scenario, except that we are not using a time history, but we're using a monotonously increasing load to simulate a pushover kind of effect. And we also tried this with a fictitious building with one of our index buildings with a rigid roof, and we can still see the same effect. So now going to one of our actual buildings, this is IB2 loaded in the Y direction, and see how this performs. This is the strain contours, principal strain contours that you see, and this would be the curve that is the force versus displacement at the top of these 2 out of plane walls. And this is the top view of the analysis. So if you look at it, the curve keeps progressing even after parts of the buildings are practically collapsed. So we need to identify a position at which you could actually say, okay, I'm stopping my analysis at this point. So we consider some criteria for this. Now, we go into each of these buildings and analyze their behavior separately. So for IB1, in both X and Y directions, the behavior is very much local. The wall portion above the lintel band just overturns and collapses, even before mobilizing rest of the capacity of the building. And in the case of IB2, you still have the cantilevering OOP mechanism, out of plane mechanism, but there is some horizontal action that is forming between, in these out of plane walls. Still, the in plane walls in this direction is these, and in plane walls in this direction are these, and they remain almost intact. Coming to the IB3, you have a much better global performance when loaded in X direction because of the better confinement, and the out of plane walls are able to transfer the loads to these in plane walls, and you actually have the shear cracks that you would expect in a very typical confined masonry building with rigid roofs. So the confinement is very effective in the X direction, but when it comes to Y direction, it's not as effective. So we also check the participation of the walls in each of these buildings and see that in IB1 and IB2, the in-plane walls do not participate at all, while IB3, it does. So it comes to a question of what do you consider is your engineering demand parameter? If you go with the average, it would be underestimating the displacement capacity in these 2 cases, at least. And if you go for the out of plane maximum displacements, that would be kind of overestimating. So we looked into this, and we decided to go with both approaches and have a comparison. So this would be the capacity curves generated using average top displacement or drift with base shear coefficient. That is the base shear accumulated on the whole of the building foundation. And this would be the maximum or the out of plane top drift versus the base shear. So you can see that from IB1 to IB2 to IB3, the capacities keeps steadily increasing as we would expect, and also the displacement capacity also increases. when you compare in the CC average or the average top drift approach. And in the case of IB2X, it is very significant improvement when you use the other approach, the CC max approach. Sorry. Now we gather these data from our curves and go on to see which could be used for each of these buildings based on their behavior. So we have seen from previous figure that IB1 and IB2 mostly behave like a local out of plane behavior, while IB3 has a better global behavior. So now we come to defining the performance levels, slowly coming to our fragility analysis. So this is another area of challenge where you have three different buildings, but you need to be able to compare them for your purposes. And we find that the drift limits are varying considerably between these two approaches, and also between IP and OOP mechanisms. Because the OOP mechanism is mostly related to the rocking of the wall, it can have a considerable deformation before ultimate collapse. And the in-plane mechanism is mostly associated with shear of these walls. And we have gone to some literature to see the usual ranges of these buildings in these two mechanisms and compare with what we have observed from our analysis. And now we have defined three performance levels: the immediate occupancy, life safety, and collapse prevention. So these are basically from the way the damage progresses. For example, the immediate occupancy is defined as the formation of flexible cracks on the out-of-plane walls, which are normally the first ones to form. And the life safety is defined as the formation of significant cracking, open cracking. And the collapse prevention is when sufficient number of major cracks are formed to form a local or a global mechanism. Now you have all the inputs that you need for a fragility analysis. So you could use something like an N2 method using a fleet of ground motion records and your capacity curve in the acceleration displacement spectral space to derive your performance points. And you have these drift limits that you have defined for each of these performance levels. And we could use a simple least square error method to derive the fragility parameters of the log normal distribution. So from this, we have come to these fragility curves from both the approaches. And we see that you could see the improvement from IB1 to IB3 as we observed before. There is slight deviation in this trend for IB3 and IB2. As you can see, the IB3 with the dotted green lines falling behind the dotted blue lines, at least in IO level in the CC average approach, and IO and LS levels in the CC max approach. This is attributed to the lower initial stiffness that IB3 has in Y direction, and also the way that we have defined the immediate occupancy levels. And we see that the IB1 has similar performance in both X and Y. Both these red dotted and solid lines are always similar, but IB2 and IB3 are evidently more vulnerable in Y direction, that is the dotted ones. So what we see is that just improving the confinement of IB3 alone is not providing much of an enhancement to its seismic performance. So we need to consider additional measures such as adding cross walls or having stiffened diaphragms, or at least improving wall density by increasing the wall thickness. Now coming to it's always easier to compare and have a meaningful comparison between different buildings and different techniques when you compare it at a particular level of intensity. So we look at the maximum considered earthquake at 0.36 G for this location, and we see that in most cases, the CC average approach predicts a more conservative result, while we know that the CC max approach is capturing the behavior in a better way. So we do this analysis for for two of our intensity measures, that is PGA and spectral acceleration at the first fundamental period. And we compare them at the same maximum considered earthquake to see, just to see if any of them has a better performance or which is more suitable. And we see that the assay-based fragility curves give you a higher probability of exceeding individual performance levels when compared to the PGA. But when you compare the dispersion of both the IMs, dispersion of the curves based on both the IMs, they are not consistently better than the other. So we conclude that both are suitable for this kind of an analysis. Now, again, here we can see more clearly the conclusion before, that the CC average approach is consistently more conservative. Here, we have now everything that you need from a fragility analysis. Next question is, how do we use this? So our ultimate aim is to look at the school compound as a system and assess the system performance from various factors based on the fragility curves that we have defined or derived. So if you look at a particular example where you have 3 buildings in a campus, each of them having single or multiple functions like classrooms or offices, and they all feed into the final ultimate system. So for the system to be performing intact, all of them have to be performing in a certain defined way. So you could have this earthquake hazard input into the system, and now you have the fragility curves, and see how the system performance changes for any scenario that we could imagine. For example, we consider another system where you have 4 blocks instead of 3, and see how the probability of teaching in classrooms is changing with this just one change. And also this is very useful if you are considering different retrofit options. For example, you have 3 IB1s in the campus. You would want to do a retrofit so that all of them comes to IB3 level of performance, and see how the final system performance changes, or what are the inputs, what are the benefits in a quantitative term, and which can also easily be extrapolated into financial terms. This is one of the application, and we are also extending this approach into a multi-hazard scenario where you have combined flood and seismic loading, where we can define the kind of loading like a building is weakened by years of flooding and then affected by an earthquake. And this kind of a scenario, there are more complicating factors that are coming into picture, such as both the hazard inputs and also more uncertainties. And the definition of functionality is very important when it comes to floods, because we don't necessarily need structural damage to be for the functionality to be lost. So I think this would give you an idea how we would be using the fragility curves that are being derived here. With that, I think I have almost covered everything I wanted to discuss today. Yeah, the first question is, yes, they are confined masonry. And with the developed modified taxonomy, we now have a measure of to what extent they are confined masonry in terms of their seismic design levels. Now, yeah, using this new technique of applied element method for modeling, it was very new, and it was time taking, but it was very interesting to learn and analyze using this technique, especially because you can go till the final collapse of the buildings. The next challenge was to use the pushover analysis technique for buildings with flexible diaphragms, and the idea of using the ground acceleration instead of a force or a displacement based regular pushover. And again, the comparison between 2 EDPs and 2 IMs that we can use for a fragility analysis just shows you how sensitive these procedures are for the assumptions we make in the analysis. And we say that both PGA and spectral acceleration seems to work fine for this kind of an analysis in the case of IM. And for EDPs, we see that the CC max would be capturing the behavior better. But if you want to be more conservative, you need to go for the CC average approach. So I would stop here and leave it to the audience. If you have any questions or any clarifications on this, please.
Thank you very much. Very interesting. As always, feel free to unmute yourself and ask questions, or you can type it in the chat. Anyone has any questions? I will start with the question, how did you define your collapse?
Could you please repeat? How do you find, how do you define?
How did you find the collapse damage state? So I was looking at the model that you had, and I could see that some of the walls were fading in out of plane, some of them were continuing even after the out of plane.
Yeah.
Don't you stop the model when the first out of plane happens, and don't you consider that as collapse, or is like more complex than that?
No, it's mostly what you just said. Like even though the in-plane walls stay intact, it doesn't really matter as long as the out-of-plane walls are completely or partially collapsed. So especially considering that we are looking at school buildings, and life-threatening damage is what is considered as collapse to be very specific, because even the top portion above the lintel band, if it falls and collapse on into the building, inside the building, that's sufficient to be life-threatening. So the criteria we used is when you have sufficient separation cracks. So I forgot to mention this maybe. The red lines, if you can see in this figure, are separation cracks. Is it visible? So you can see these portions falling off in the IB1 and as well as in IB2. But in IB3, you have better, like at least in X direction, you have both walls participating and failing almost at the same time, but not in the case of IB3Y. So in any case, we look for sufficient number of separation cracks that are formed that would form a collapse mechanism. And also beyond that point, the behavior becomes unstable.
Okay, this extreme loading software, so it continues the procedure of the push even if you have very extreme drift. So I'm sure like in an out of plane, you have like ultimate drift. So, but the software continues until you see the separation of the bricks.
Yeah. So
that's interesting.
Yeah, so that is one good thing about this, is that you can have you can define when you want to have that separation as well. So for each of the material, you define your separation strain based on your element sizes and how long it can actually, the crack can form before two elements separate. So once the crack is formed to that extent, you expect to have a separation between two brick elements, for example, or any two elements. So until that defined level of separation strain is arrived, it keeps loading. So in this case, especially because we are giving the ground acceleration, it's a force-based approach. So we do not have the control over the degrading portion of the curve, if you would say.
If I can just add here,
yes, please.
hello again. Yes, this particular way of modeling masonry, it's extremely important in order to have a good understanding of how masonry structures behave, because masonry structures are by default highly redundant, because all the material can perform the same functions. So in a wall, in order to transfer the gravity load and the lateral load, you don't need all the joint and all the bricks to work at once. It is because usually when they work all at once, the level of stress and the level of deformation is very modest with respect to their capacity. So when a number of diagonal or vertical tensile crack develop, as you can see in the pictures that Ahsana is showing, there are still load paths that can be identified in any of these masonry portions. And those load paths are allows to transfer both vertical loading and so gravity loading and lateral loading as we simulate the earth. Of course, once, however, the geometry of the deformation is such that any of the portion of these walls become unstable, then we cannot consider these as still performing in a structural sense. So that's where we then decide that the analysis is not meaningful anymore. But because this particular software actually looks at, for instance, formation of debris or rock, fractured rock movement and so on, allows you to actually look at the dynamics of that collapse mechanism occurring. And so we can also learn very much from that in respect to the real formation of collapse mechanism in masonry structures. That's why we let the analysis run until we have a pile of bricks, basically.
Yeah. And I am very sorry about this because I forgot to mention here that these are deformations magnified 10 times. So if that gives you a wrong impression that these are the actual deformations, I'm very sorry. But the dimensions of the deformations that you can see in these are correct as it is. So, and the other thing, as Dina mentioned, this software is very specifically and extensively used for blast simulation and progressive collapse, for example, and it does really go to that extreme loading.
Interesting. If anyone has any question, please feel free to unmute yourself and ask, or you can type it in the chat and I will read it aloud.
Roberto here. Thanks, Ahsana, for the nice presentation.
Thank you, Roberto.
And my question is, are you planning to check against time history analysis with this software? Because it seems very, very promising.
Yeah, I mean, that is one of our aims to get there. So this is, we haven't tried on the buildings yet, but we did try time history analysis on some of the walls at the time of our validation of the numerical software for masonry, especially confined masonry, and it does perform very well.
Okay.
Yeah.
No, I mean, the thing was, let's say, for example, you get ground motion with a very high frequency, for example, that can excite your in-plane walls more than your out-of-plane walls. In this case, your capacity curve would change, and so your performance point, and so on and so on. But I think by comparison, you can understand where the error lies and where you can trust this simplified approach, which is great. And when you can...
Okay. Yeah, just to be clear, are you suggesting you do a bidirectional analysis at the same time? I mean, we were only doing a unidirectional, either X or Y.
Even just monodirectional.
Okay.
If you go to slide 13, the previous one.
Yeah.
So, for example, in these in one direction, if you get a very a ground motion with a high frequency, you will excite, for example, your in-plane walls rather than, let's say,
out of plane walls,
out of plane ones, and vice versa. So if you perform the pushover by assigning different loads, you can mimic this. Maybe you will need to but you can get the same result, or at least you can go close to the time history result.
Okay.
Yes, if I can intervene here.
Yes,
so,
please.
Yes, because we have done this with other type of, we are using this in a number of different projects, this particular modeling technique. And we did this quite extensively with unreinforced masonry structures. The particular, let's say, positive aspects of doing the ground acceleration pushover is that you don't actually redistribute loads. So it's not a traditional pushover analysis where you beforehand determine a relationship between the forces, the distribution of forces that you will have in both height and horizontal plan, depending on initial stiffness. Here, you just input a ground acceleration. That ground acceleration is automatically redistributed to each element of the structure according to the, of course, it's a static equivalent analysis, so it will still take the stiffness metric and the mass matrix in order to determine the redistribution, but will be then at each increment of loading, it will be then directly related to the progressive failure of the elements. So there will be an automatic redistribution of forces. It's still not exactly nonlinear time history analysis because there is it's missing the dynamic amplification and the dynamic excitation, of course. But on the other end, we have done some simulation, and I don't know if Rohit is around at this particular moment in time during the seminar, possibly not. And we have also published some work on this. This particular type of pushover analysis best meets the as the best approximation with the nonlinear time history analysis, and takes into account the different stiffnesses of the two set of walls, to put it simply.
Thanks.
You're welcome, Roberto.
I can see someone raising hand. Lopez, if you want to unmute yourself.
Hi, yes, thanks. Jorge Lopez from Arab.
Hi, Jorge.
I was wondering if, you know, I think a lot of the work you've been doing was on existing school buildings.
Yeah.
And I was wondering if there's any intention from the results of your work to draw some conclusions and some recommendations for the design of new buildings, perhaps new school buildings using this system, or design of retrofit techniques. For example, you mentioned that adding a ring beam at the top of the building didn't quite help much in the short direction. So yeah, I was just wondering, you know, what sort of recommendations you can, or you know, if you're planning to give any recommendations as a result of your work, or if you can give some now, for example, if you had anything.
Hi, thank you for your question. Within the span or within the duration of the PhD project alone, I don't know how far we would get to the retrofitting aspects of the buildings, but our attempt was to assess the available seismic capacity of the existing non-engineered confined masonry buildings in the first place. So we can see that how much of an influence each of these components have in their available seismic performance. And it definitely does have a lot of capacity improvement from IB3 to IB1 to IB3, even though the displacement capacities are compromised. If you see the maximum capacity base shear in terms of base shear, it's really much higher than the one or with poor connections and poor design level. And also we have a project that we're planning as an additional project with the EFIT grant, which would specifically look into the retrofitting aspects. So comparing the practically available sources or methodologies for retrofitting these structures to improve their seismic design level from, say, poor to at least medium or high. So one of the things that we have concluded from the analysis so far is that just having the roof band is not sufficient to provide enough seismic performance in both directions, and it has to be supplemented with at least cross walls or horizontal bracing elements at the roof level that would improve the lateral behavior of these structures in the y direction. So that the unrestrained length of the long wall is remaining as the most critical feature of these buildings, if you look into the larger picture. And this is also part of many other projects on school buildings that is now going on within EPICentre and within CGE. And we do hope to have some recommendations for the construction of new buildings, especially in this situation that, as you have seen in the very beginning, there are many school buildings that are now being constructed using confined masonry. And if you really look at them closely, they're not typical confined masonry buildings. They do have large openings and deviations from the standard. So it would be very useful to have a recommendation for schools separately.
Thank you.
Again, if I can just add very quickly that,
yes,
because I don't want to take time from more questions, which there are. We are doing quite a lot of work in this, in the sense of recommendation for strengthening within the GPSS, the Global Program for Safer Schools, which is a World Bank program, and the glossy library things of outcomes that we are particularly involved with. So I wish to direct you towards the glossy and the GPSS to say more outcome on also different building typologies, both reinforced masonry and reinforced concrete, as well as confined masonry.
Great, thanks. Thank you.
Newman, I can see that you have raised your hand if you want to. Thank you.
Yes, Arish. Thank you, Ahsana, for a wonderful presentation.
thank you.
You have explained things in a very simple manner, and it was easy to observe the knowledge that you have produced. My question is around the validation of this. You have validated an experiment in the in-plane direction, right? So my question was about the out-of-plane direction. Did you happen to also validate that, or that is not required for this particular study?
We have done, in the very beginning, we have done extensive validation trials using in-plane experimental results that are available in the in-plane direction. So
Right.
it's very difficult to find an out-of-plane experimental study on out-of-plane behavior of confined masonry walls. I'm not saying for URM walls. And we haven't really done a validation for the out-of-plane walls alone.
Right, right. And just a quick another question. You have used applied element method, right, rather than finite element analysis.
Mm.
So first, what was the reason? And second one, how many elements were there in one building type, for example, roughly? I mean,
okay.
Like just a rough idea of.
Yeah, I could just give.
Sorry, I'm asking this because I'm also a
PhD
student working in this masonry thing. Yeah.
So the first instant why we use this is we know that finite element analysis is very good in the continuum range of analysis. So once you get into the separation of elements, you have limitations. You have although you have approaches like smeared crack approach, or you define predefined crack locations or crack pattern. The good thing about the applied element we found is that it is you don't need any of that. So the issue, and it is very much intuitive. You can model the masonry as it is, so with the actual configuration of bricks and mortar, without having to predefine the cracking or predefine the failure mechanism. So which we found is very very suitable for masonry modeling for like more than any other structural system. And this was a very new technique, and the software itself is very new, and we are exploring and even adding value to their new additions and new versions so that better can be done. And I would, I think for your question, second question on the number of elements, I will get back to you. Like it just would take 2 minutes to open the file.
No worry, I can get in touch with you on email or something, no problem.
Yeah. So if you have anything very specific, you could get back to me even later if you need any assistance with this.
Sure. Thank you so much.
Okay, perfect. We're coming to the closing. Again, I'll thank Ahsana for an interesting presentation. If you don't mind, I'll just talk a little bit about the coming events that we have in March mainly. So today we had seismic analysis.
Just a second before you go on to that. So this is just a plug for the MSc students. So for we will be speaking much more about masonry in the second part of the course on structural vulnerability and resilience. But for the ones of you that are interested in this type of work, we are also offering the MSc projects. And so get in touch if you want to pursue work in this field of seismic engineering. That's it.
Perfect. Thank you very much. So yes, today we had the seismic analysis of confined masonry buildings with flexible diaphragms. Thank you, Ahsana, for presenting. Then we'll have a break and we'll come back on 3rd of March when Dr. Gemma Kremen will be discussing about a decision-making methodology for risk-informed earthquake early warning. The week later, we will have Felipe Rivera talking about moving beyond safety and fragility towards equitable seismic risk management. And the week after that, we will have Dr. Jion Bayan talking about matrix-based Bayesian network for reliability analysis and decision-making of large-scale engineering systems. And the last week of March, we will have Andrea Francini talking about probabilistic optimization of seismically excited cable-stayed bridges. So, and then we'll go to Easter holidays. With this, I want to just say that Happy Chinese New Year to all of our students and staff as well. Hope you enjoy it. We'll have the reading week as well, so you can relax a little bit. One last point is, as always, majority of our seminars are getting recorded, and you can always find them in EPICentre website as well as our YouTube channel. And with that, I'll just end the session. If you are interested, please become free student member of the institutes as well. So thank you very much again. Thank you for presenter Ahsana as well. And yeah, we'll see you in March.
Thank you, everyone. Thank you for all the questions. And I will get back to Newman. I think it was Newman who had the question, yeah?
Yes.
Yeah, okay. Thank you so much.
I can see Jonas had a question as well. So Jonas, please, if you want to discuss it with Ahsana later on.
Yeah.
Okay, perfect. Thank you very much.
Thank you so much, everyone.
See you later.